Okay, today we're talking about Chapter 5, Molecular Structure. Let me just start by saying some of the things that we won't be talking about, and that is the molecular orbital theory. So sections 5.5, 5.6, and 5.7 will not be included in our discussion of this chapter. We'll focus just on valence bond theory, being able to predict molecular shape based on that theory, and then a little bit about the hybridization of orbitals. So molecular shape is based on this model called the Vesper model, which is valence shell electron pair repulsion model, and it is described as how electrons can be thought of as occupying these charge clouds, and that those charge clouds repel each other because obviously they have the same charge, and they try to stay as far apart as possible. And so we predict the molecular shape or geometry just based on the number of charge clouds and what shape allows us to put them as far away from each other as possible. So if you think about it that way, it'll make sense why we end up with the shapes that we do and the bond angles that you see that result as well. So just based on geometry. So one of the things to be able to do first is to be able to look at a compound and identify the number of charge clouds it has. So that's a critical skill for this chapter. In order to do that, you're looking at the central atom of the compound, and in all of these cases, you'll be looking at compounds where there is just one central atom, and then the rest of the atoms are bonded off of it. So you'll notice that pretty much all the compounds we deal with are that way. That doesn't mean that all compounds are that way, it just happens to be the ones that are sort of simplest to predict shape, and so that's what we use. So in this example, these are two charge clouds examples. Again, the central atom here is carbon, and we're looking at the fact that carbon is bonded to two other atoms. And so when we look at the shape that it will have, we consider the carbon bonded to the oxygen on either side, that each of those is a charged cloud around carbon. So in order to separate those charged clouds as far apart from each other as possible, they make a linear shape so that the bond angle between the carbon and oxygen is 180 degrees. So one of the things, there is a table that we'll get to in a moment that's in your text as well, is to be able to look at a compound, predict how many charge clouds it has, what shape it will have, and then what bond angle it will also have. So those are the key components, key skills, key information to be able to predict for any compound. You can see also the other example here has hydrogen and nitrogen bonded to the carbon, again, two charge clouds. And so it's a linear molecule, and the bond angle is 180 degrees. The shapes will tell you a little bit about the bond angles and sort of vice versa. And I know you're also doing this in lab in terms of using models and building that way, so I won't spend a large amount of time on this today. So three charge clouds, we look at some examples here. Again, looking at the central atom. You can see in the two top examples, the carbon is, in the top example, the carbon is bonded to oxygen and two hydrogen atoms. So those are the three charge clouds that are around that carbon atom. And they're showing you just a top view and a side view with that compound. There are three charge clouds. This forms a trigonal planar shape. That's the name of the shape that we see here. And the bond angles are about 120 degrees. I won't ask you to predict the exact numbers that you can see there, but that you can predict the 120 degrees from that molecule. And the differences are based on the fact that the two hydrogen atoms will repel each other with slightly less force than the hydrogen and the lone pair. And so that's why you end up with a larger bond angle there. The one on the bottom, notice this has three charge clouds, and here's where we get into identifying charge clouds and the difference between that and the types of charge clouds and what types of shape you see. So there are three charge clouds around sulfur here. One of the charge clouds, or I should say two of the charge clouds, are those oxygen atoms that it's bonded to. The third charge cloud is the lone electron, or I shouldn't say lone, the electron pair that is electron pair or lone pair that's located on that sulfur atom. So any lone pairs or any bonded atoms are what you include in your charge clouds. So there are 3 charge clouds here. However, when you consider the shape of the molecule, you are only considering the bonded atoms. In this sense, so think about actually making a molecule here. You wouldn't include that lone pair as sort of part of the molecule shape that you're showing. It does impact the overall shape of the molecule, but it's not included in drawing the molecule or showing the shape. So the takeaway here is that when you have these 3 charge clouds and one of them is a lone pair, you end up with a molecule that has a shape that is called bent. And you can see that SO2 molecule there has a different shape than what you see up above because it's only bonded, that sulfur atom is only bonded to 2 oxygen atoms. So 3 charge clouds. The one on the top is 3 charge clouds that are 3 bonded atoms. That type of shape is trigonal planar. 3 charge clouds where you have 2 bonded atoms and 1 lone pair, the shape is bent. And again, that table will also show you the differences here as well. When we get into 4 charge clouds, if you think about the shape that might result here, trying to get, again, those electrons as far away from each other as possible, you put the central atom in the middle there, and then the charge clouds at the 4 corners, or points, if you will, of a tetrahedron. That's how you end up with the most space between those. I should back up a moment. I didn't mention on the bottom here, the angle. Notice the angle for the 3 charge clouds. It doesn't matter whether it's the one on the top or the bottom. The bond angle there is 120 degrees. Okay, so bond angle here for all of your atoms is 109.5. And here's an example, or several examples. So methane at the top, 4 bonded atoms, and so that shape that you end up with is tetrahedral. Bond angles are 109.5 degrees. The ammonia molecule in the central part has just 3 bonded atoms, so its shape is trigonal pyramidal, and you can see the shape there on the far right. So that lone pair is acting to make the shape of the molecule, but it's not shown in the overall drawing because the lone pairs don't have a physical shape to them. Water molecule on the bottom has 2 bonded atoms and 2 lone pairs, and so this forms again a bent molecule, and bond angle there is 104.5 degrees. Actually, let me back up. So these 4 charge clouds, when you predict these, it's fine for you to predict 109.5. They're showing the smaller angles, and that's again the difference between the lone pairs and 2 atoms. 2 atoms generally repel each other with less force than a lone pair and an atom will. So that's why we end up with the different numbers that you see. 5 charge clouds. The geometric shape here to get 5 charge clouds as far away from each other as possible is a trigonal bipyramid that you see on the far left. And then you can see a side view and top view here. And the angles, so the angles between the central atom, you can see the one on the top, the central atom, and the one on the far right are 90 degrees, and then the ones around the equatorial positions are 120 degrees. So the axial positions are the ones that are pointing up and down from the central atom, and the equatorial positions point out from sort of if you think about drawing an equator around that central atom, they point out from the 3 positions from that central atom. So here's an example of one. Again, 5 charge clouds, 5 bonded atoms, and the shape here is trigonal bipyramidal. Here's an example where we have 5 charge clouds, but notice we only have 4 bonded atoms, and so the shape that we end up getting is called a seesaw. 5 charge clouds, 3 bonded atoms, we end up with a T-shaped molecule. And 5 charge clouds where you have just 2 other bonded atoms ends up being linear. You can see in the middle where those lone pairs are around the equatorial positions. So the two other iodine atoms are on the axial positions on either end, so they form a linear molecule. I'm actually just going to get to where that table is in your text. So page 174 has all of these that I'm showing you. The last one we'll discuss here are 6 charge clouds. That's the center of a regular octahedron, and you can see you've got 2 axial positions here and 4 equatorial positions. So if you notice with the 5 charge clouds, you had 2 axial positions and 3 equatorial positions. And so now you've just essentially added a 4th equatorial position to make that shape. Here's a molecule, 6 charge clouds, all 6 bonded atoms, and so the shape is octahedral. 6 charge clouds, 5 bonded atoms, and in a lone pair, and this forms a square pyramidal shape. Again, 6 charge clouds, 4 bonded atoms is a square planar. Those bonded atoms end up in those 4 equatorial positions. I should have said by now sort of how we predict these shapes is based on where it's most stable to put both the lone pairs and the bonded atoms. Because, there's more repulsion between lone pairs and either a bonded atom or another lone pair. That's what impacts our overall predictions of these shapes and impacts where we end up putting where we end up seeing the atoms in the overall molecule. And again, this is the table I was referring to. So just in terms of reading this, you can see on the far left it indicates the number of bonds and then the number of lone pairs and the number of charge clouds. I find it easiest to sort of start in the middle there with the number of charge clouds, and then you can see the different arrangements you could have. So with 3 charge clouds, you could have 3 bonds, in which case that shape is trigonoplanar, or you could have 2 bonds and a lone pair, in which case that shape is bent. And we've gone through all of these examples, so if you wanted to go back and look these over, you could. And on the far right gives you the examples that we just looked at. And then here's the same thing for 5 and 6. So we use this okay, so we use these, what we know about lone pairs and what we know about bonded atoms to form another theory that's known as valence bond theory. And this is how we can show how these electron pairs are actually shared in a bond. So this gets away a little bit from the shape, but obviously is important in understanding how we end up with molecules that are covalently bonded. And if you look at, so think back to when we talked about orbitals. If you look at 2 hydrogen atoms coming together in a hydrogen molecule, each of those hydrogen atoms has a single electron in a 1s orbital. And when they come together in that bond, one of the electrons of one hydrogen atom will have an opposite spin. That's why you see the arrow pointing up from the hydrogen in the other atom. And so we see what happens here when that hydrogen molecule forms is those 2 electrons come close to each other. That overlapping spin attracts them together in that bond. And you can see on the far right how we can represent that. So again, you can see the arrows up and down representing the 2 electrons that are being shared in that bond. And more importantly here in terms of the theory, each of those are in a 1s orbital. And so what you end up seeing is that the overlap between each of those 1s orbitals is where that bond is forming. And so one of the things to take away from this is to be able to predict the orbitals that are overlapping in a bond. So if I were to ask you what were the bonds that we see in the bond between an H2 molecule, that covalent bond, you would say that that covalent bond results from overlap of the 1s orbital of one hydrogen atom and the 1s orbital of the other hydrogen atom. If you look at, say, 2 fluorine molecules, their valence electrons are located in a the 2p orbital. It doesn't matter here if you chose a 2px, 2py, or 2pz. We know that those are all degenerate orbitals. They're the same energy levels. Importantly, though, you can see one fluorine atom has its electron in a certain direction or a certain spin, and the other one in the opposite direction, the arrow in the opposite direction indicating opposite spin. And so what happens here, again, the overlap of those 2p orbitals of each of those fluorine molecules forms that covalent bond between them. When we see this type of overlap, this is essentially a single bond, is known as a sigma bond. So this isn't really described that way in your text, but it is how we think about these bonds. So anytime you see a single bond, and that's what is representing in both of these cases, those are known as sigma bonds, and that's that overlap that we see between those two different orbitals. So this I've mentioned sort of mostly, but here's kind of the main pieces of this theory. So these covalent bonds are formed by overlap of orbitals, each of which contains an electron of opposite spin. Those two overlapping lobes must be of the same phase. That means they're the same type. You wouldn't have a 2px overlapping with a 2py of the other atom, for example. Each of the bonded atoms maintains its own atomic orbitals, and the electron pair is shared by both atoms. That's sort of what we mean by a covalent bond. The greater the amount of the overlap, the stronger the bond, and vice versa. So if we look at, for example, methane, so I should back up. So valence bond theory works for most of our fairly simple atoms in terms of the bonds and that the overlap, what we just talked about here, in forming sigma bonds. When we get to more complicated examples, which in this case we'll see in methane, we have to introduce the concept of hybrid orbitals, and we'll talk a little bit about those. And it's essentially the valence bond theory and adding in hybrid orbitals that allows us to explain how the bonding pattern in most molecules occurs. Molecular orbitals come onto the scene for more complicated molecules that we won't be talking about, but that orbital theory is used for those. So if we look at methane, if you look here on the left, and you can see the ground state electron configuration for carbon. This is what you would have drawn for carbon, and you would see that it has just those 2 electrons in the 2p orbitals that would be available for bonding. But we know that in methane that carbon is bonding to 4 hydrogen atoms, so we need to explain how that happens. Not only do we know that, but we know that the bonds in that methane molecule are all of the same length and the same strength. So that means that it has to result from electrons that are all at the same energy level. And that's not represented here. Okay, so even if we do this excited state electron configuration you see on the right, you'll notice we have 3 electrons in 2p orbitals and 1 of those electrons in the 2s. Those are at different energy levels. And that would not be enough to explain the bonding and what we know about methane, in that the bond lengths and strengths of each of those bonds are identical. So they must result from electrons overlapping in the same energy level. And so this is what brought about this hybrid orbital theory and helped us to explain why we see the different bonding in methane. So again, we have 4 non-equivalent orbitals. The 3 2p orbitals are equivalent, but the 2s is not. And so what we do here in terms of forming hybrid orbitals, I like to think of this as, think of a large pot. Like maybe if you go camping or something, you make a stew, or like at Halloween, they have those pots that, witches have, or whatever works for you. Think of a pot. And if you think about throwing in the orbitals that you have available. So in this example, we're going to throw in that s orbital, the 2s orbital there, and 3 p orbitals, right? So the important part here to figure out the type of hybrid orbital you get is just the type of orbitals you're throwing in the pot. So we're throwing in an s orbital and 3 p orbitals. Hopefully you're still with me. So an s orbital and 3 p orbitals go in the pot. So that's a total of 4 orbitals that we threw in. And we need to get some equivalent orbitals out, 4 of them. And so what we do is we pull out 4 equivalent orbitals, and all of them are said to be sp3 hybrid orbitals. Specifically 2 sp3 hybrid orbitals, the 2 meaning the energy level that we're at. Okay, but the sp3 is the hybrid part of this. So where did that come from? So the sp3 came from the orbitals we threw in the pot. Look back, we threw in an s and 3 p orbitals. And so we end up with sp3 hybrid orbitals. So the name of the hybrid orbital we get comes from the orbitals we threw in the pot. I'll give you another example in a minute. Hopefully that analogy works for you. I found for most students it's, this is such an abstract concept that having something that you can visualize helps. So we end up with 4 equivalent orbitals here, so that's important. They're all sp3 hybrid orbitals, each one of them. And they're all at the energy level, the second energy level. And so now what we can do is we can put all 4 of those electrons for carbon in those 4 equivalent orbitals. And now we can explain how that carbon bonds to hydrogen. It's important to point out here that notice we didn't hybridize all of the orbitals of carbon, just the ones we needed to, and just the ones with a single electron in them. So that's the same thing. So we still have that one s orbital. So we still have that one s orbital in carbon. That hasn't gone away, or we haven't done anything to that. It's still there. So here's a visualization of how we make these hybrid orbitals. So if you look on the left, those are the orbitals we threw in the pot. The 2s and the 2p orbitals. And we hybridize them, and we end up with 4 equivalent orbitals. They're all called sp3 orbitals, and they all form at the corners of a tetrahedron. Why? Because that's essentially 4 charge clouds, and so in order to put them as far away from each other as possible, they form a tetrahedral shape. So you can see we're sort of folding back on what we just talked about before. So the bond angles are 109.5 degrees, as we'd predict from a tetrahedron. So here we put it all together. So the carbon has its 4 valence electrons in each of those sp3 hybrid orbitals. And again, we had to do that because we needed 4 equivalent orbitals on carbon. Hydrogen has its electron in the 1s orbital. We don't have to do anything to that because that's all it has. Okay, we don't need to form any hybridization there. And then on the far right, it shows you what's happening here in the overall bonding of this molecule. So you can notice that each carbon-hydrogen bond results from an overlap of the sp3 hybrid orbital from carbon and the 1s orbital from hydrogen. And that's the type of thing to be able to explain if I asked you to explain what the bonding pattern in methane was. So between every carbon and hydrogen molecule, that bond results from the overlap of the sp3 hybrid orbital, the electron in the sp3 hybrid orbital from carbon, and the electron in the 1s orbital from hydrogen. There are other kinds of hybrid orbitals that we can get. Excuse me. And I'm actually going to skip this for now and may come back to the shapes in a little bit. I will come back to all of this, but here's the part that's sort of most important in terms of one of the things to be able to do is to look at a molecule, figure out what kind of hybrid orbital it would have. Okay, and so this table is something to either have on your exam sheet or memorize. It's really not that much information here. But if you have 2 charge clouds, so you need to form 2 equivalent charge clouds. So typically in that case you have a lone electron in an s orbital and a lone electron in a p orbital. That's how that would result. So in terms of what you're throwing in the pot, you're throwing in an s orbital and a p orbital, because one electron was in the s and one was in one of the p orbitals. So the hybridization here is sp. So you can either memorize this or you can use the pot analogy to figure this out. So 2 charge clouds, hybridization is sp. That means that each of those, you'll have 2 sp hybrid orbitals available. If you have 3 charge clouds, you're going to throw in the electron from the s orbital, and then you'll have an electron in each of 2 p orbitals. So you throw in an s and 2 p's, so the hybridization there is sp2, because that's what you threw into the pot. And so you would end up having 3 equivalent orbitals, and all of them would be sp2 hybrid orbitals. The last one there, 4, is the one we just looked at. So if you have 4 charge clouds, you've got an electron in an s and 3 p orbitals. You throw those all in, and so you end up with a hybridization of sp3. So you have 4 equivalent hybrid orbitals. They're all sp3 hybrid orbitals. In the middle, it shows you the arrangement of those charge clouds, and again, that's just based on the number of them, based on the molecular shape that we've talked about before. So 2 charge clouds, you end up with linear. 3 charge clouds is trigonoplanar, and 4 charge clouds is tetrahedral. Now I'll go back a little bit to these this other information. Let's see. So here's showing you an Here's showing you an sp2 hybrid orbital. So again, that's where you have an s and 2 p orbitals. So here's the sp2 hybrid orbital. So you've got an s and 2 p's, so you end up with 3 equivalent sp2 hybrid orbitals. And you can see those there, the green spheres that would lie around the equator. Another thing to point out here is because we put an s and 2 p's into the pot, we still have a p orbital that's left. And that's what you're seeing there in that shape on the right. So there is a p orbital that's left there, and that will come into play sort of in the next part here. So if we look at if we look at a molecule where we have a multiple bond, and that's what's being shown here. So the 2 carbon atoms that are being bonded have a double bond between them. And so the way that we visualize what's happening here, or understand what's happening here, is that double bond between the 2 carbon atoms. The first of that double bond results from an overlap between the each of those sp2 hybrid orbitals. And that is what is known as a sigma bond. So recall back when I said that single bonds are sigma bonds. The same thing applies here when you're looking at a multiple bond. If you can think about a multiple bond as being no more than just 2 or more single bonds, the first of those is a sigma bond. I know this is kind of an abstract concept here, but the first of that multiple bond is a sigma bond. If we were looking at a triple bond, the first of the triple bond would be a sigma bond. And then the second bond of that double bond actually results from the overlap of those p orbitals that are left. Recall when we looked back, we had 3 sp2 hybrid orbitals. So essentially the molecule you'd end up here with has hydrogen usually bonded to those other carbon atoms. They're not really shown here, but that might have been a little bit easier to understand. Anyway, there's a carbon-carbon double bond in the middle, and the sigma bond results from the overlap of those 2 sp2 hybrid orbitals of each of the carbon atoms. The double, or the second of that double bond, results from overlap of the p orbital, which is shown on the top and the bottom. Remember, the p orbitals have 2 lobes to them. So the red on the top and the blue on the bottom are showing the overlap of that one p orbital and the other p orbital in the other carbon atom. And that's what forms that second bond. This is just showing you how you form an sp hybrid orbital. Again, an s and a p in the pot, and you end up with 2 equivalent sp hybrid orbitals. They lie along a line, form a linear relationship to each other. And then again, you still have those 2 unhybridized p orbitals that are left, and you can see they're represented there in the red and the blue. This is showing a triple bond. So again, the first of that bond is formed by the overlap of each of those sp hybrid orbitals on the carbon atoms, and forms the sigma bond. And the second and third of the multiple bond are pi bonds. I should have mentioned that before. So when we look at the carbon-carbon double bond, the overlap of the hybrid orbitals forms the first, or the sigma, of that double bond, and the p orbital overlap forms the pi bond. So a carbon-carbon double bond has a sigma bond and a pi bond. A carbon-carbon triple bond has a sigma bond and 2 pi bonds. And this is just how we sort of denote these multiple bonds. And they're the same to each. Okay, and that's essentially where we'll end. Here's that table that I showed you before.